Hello friends, I'm Nikita and you are watching Prepare for GATE. Moving with the content of electronic devices, energy band diagram, carrier transport, generation recombination, Poisson and continuity, PN junction and other diodes, and the implantation process at last. In this lecture tutorial, we will discuss PN junctions in a diode, LED, photodiode, solar cell. Moving with our first topic, that's PN junction. PN junction is formed after the combination of p-type and n-type semiconductor through thermal oxidation or photoconductivity. A region of PN junctions will form due to charge, carrier, and electric field. The electric fields will form indirectly from positive to negative. The width of the field is formed at the junction. In transition region of it, the electric field is the gradient of contact potential. At equilibrium, the drift and the diffusion current just balance, which gives us the equation that mobility upon diffusion coefficient is equals to 1 upon the concentration of minority carriers and a differentiation in that concentration. Now solving further, if we kept from Einstein relation that mu p upon dp is equals to q by kt dot, I think I have missed an e in here. Similarly here. Okay. This E will be equals to dV naught over dx, which is similar to 1 over concentration into differentiation of the concentration. If we integrate both the sides, we'll get V naught is kT by Q natural log of Pp over Pn. That means hole in the P region over the electron in the P region. If acceptor Na are present on the P side and donor Nd is present on the N side, then V naught is equals to kT by Q Na over Ni square over Nd. Kt by Q is natural log of any Nd over Ni square. Pp slash Pn is e to the power Qv naught by Kt, a total uncompensated charge on either side of the junction, is Qax P naught into Ne, Qax N naught into Nd. According to the Poisson equation, the gradient of electric field to the local space charge at any point dE over dx is q by epsilon p minus n plus nt minus ne. Integrating the potential difference at that point to the width of the transition, which we have got earlier, is V naught is half E into V, or half Q epsilon N dx naught N into W. V naught is 1 by 2 Q by epsilon and A N D over Na plus Nd into W square. Xp naught is actually Xp naught and Xn naught is the region of the total length on P side and total length on N side of the depletion region, which combines to form the width. The charge over N region and P region, Q of N is minus of Q A Xn naught into Nd, and Q plus is Q A Xp naught Ne. The electric field across the region E is equals to minus Q by epsilon Xn naught Nd minus Q by epsilon is Xp naught into Ne. Now look at our very interesting question. In this, there you can see there is an N plus N silicon device and is fabricated with uniform and non-degenerate doping. We have talked that degenerate doping is an intrinsic type semiconductor, and non-degenerate means that it have an added impurity with Nd1 and Nd2. corresponding to the N plus that will have more number of electrons as compared to N region. At the operational temperature T, assume complete impurity ionization, and KT by Q, an intrinsic carrier concentration is given. What is the magnitude of the built-in potential? We have known that V0 depends on both the concentration, and the magnitude will be dependent on its concentrations, which is donor concentration in one over donor concentration in another. The built-in potential is V0 upon Kt by Q natural log of Nd1 over Nd. It gave me 1.73 volts.